Bismillah Rahman Rahim. This is our online lecture due to the current conditions and the notification from the university. So we will start from the pitted tube. One section, maybe the section B, they already we go through these topics, but as a revision we will revise, and this is new for the other section. So we will start with the pitted tube. Okay, so pitted tube is an instrument to determine the velocity of flow at the required point in a pipe or a string. It consists of glass tube bent through 90 degree. You can see on the figure, this is a tube of 90 degree bent. Here at point A, this is the entry point. So you can see water is flowing in this direction. So when water enters at this point, so due to capillary action, the water will rise up. So the height that water gains depending upon various factors, the velocity definitely, and the available head. So this you can see this head H depending upon the velocity. More the head, more the velocity. So we only have to find this rise in the head, which is H. So V is equal to under root 2 GH. 2 GH. You can see in this equation only H is the variable, G is constant, so we can find the velocity. When you find velocity, so we can easily find discharge. Q is equal to A into V. If we are also considering the coefficient of discharge, we can add C as well. Okay, so this is the function of pitted tube. So this type of pitted tube you can see in the figures. Here you can see this is installed under the wings of an aeroplane. Here the same one, and many other. There are many uses of this pitted tube. So you can find here. You can see this a small nozzle on this side. So air velocity, wind velocity, we can measure by using pitted tube. And pitted tube is also used to measure velocity in the laboratories, okay, in open channel flume. So this is the formula. Okay, so related to this pitted tube, we have a problem, very basic problem. A point tube was inserted in a pipe to measure the velocity of water in it. If the water rises in the tube is 20 millimeter, this is H. So you can find velocity by the formula V is equal to 2 under root 2 GH. This is H is only the constant, but keep remember that you have to change this 200 millimeter into meters. Okay, you will get the velocity. So answer should be 1.98 meter per second. Next is flow through orifices. Orifice is an opening in a vessel or water tank through which the liquid flows out. This opening is called an orifice as long as the level of the liquid on the upstream side is above the top of the orifice. The usual purpose of an orifice is the measurement of discharge. So orifice is also used for the measurement of discharge. It can be provided in the vertical side of the vessel in the base, but the former is more common. Here you can see this is the tank, for example. This is opening near the bottom. So when you fill the tank at some level, you can see that water is flowing out like a stream. So this is called the jet. This is a jet. Okay, this is a trajectory. So this trajectory, this x distance, depending upon the level H in the tank. If level is H is low, so x will decrease. Okay, so here you can see in this jet, you can see some changes in the diameter, So the minimum diameter will be at this point near the you can see this is near the orifice. This is orifice opening, and this is the point where the diameter of the stream or the jet will be the minimum. This is point, this is called vena contracta. Here you can see. So the point on the flowing jet, the point where the diameter is minimum, is called vena contracta. Okay. And this point is usually near the orifice, because at that point the flowing water it's contracted. Okay, you can see this is point of contraction. So this point is called vena contracta. Okay, so depending upon the size, shape of the edge and nature of the discharge, we distribute orifices into various types. This is small and large, is depending upon the size. Similarly, shape, circular shape, rectangular shape, triangular shape, and shape of the edge, sharp edged or bell mouthed edge. So this is the edge, these are the edges of the orifice. Nature of discharge is fully submerged or partially submerged conditions. So we are not going into the detail of the types of orifices. So these are some important terms related to orifice. Jet of water is a continuous stream of liquid that comes out or flow out of an orifice, is known as jet of water. That is simply, as you can see, this is the jet of water. Okay. Vena contracta is the point where the diameter is minimum, the least, and the fluid velocity is at its maximum. You know that when area decreases, the velocity increases. Minimum the dia, maximum will be the velocity. So next is the hydraulic coefficients. You know, we need coefficients for because in the field we have some data which is the experimental data, and some is the theoretical data. Theoretical data means the data that you got from the equations, developed equations. And experimental data means that you have collected from the experiments and then you find the results. So sometimes, due to many factors, depending upon various conditions, the experimental and the theoretical results, they are not matching each other. There will be some little bit difference between them. So to cover this difference, we use coefficients. So for these coefficients, we have coefficient of contraction, coefficient of velocity, coefficient of discharge, and coefficient of resistance. So coefficient of contraction is the ratio of area of jet at vena contracta to the area of orifice, is known as coefficient of contraction. For example, we have this orifice, this is jet. So this dia, minimum dia, vena contracta, area of this section to the area of orifice, this is CC, which is known as coefficient of contraction. So its average value is about 0.64. So the value varies slightly when the available head of the liquid, size and the shape of the orifice. So the average value is 0.64. Coefficient of velocity is the actual velocity of jet at vena contracta to theoretical velocity of jet. Velocity at this point, vena contracta, to the actual velocity so this is the actual velocity, and divided by theoretical velocity of the jet, you will get coefficient of velocity. Okay. It is represented with CV. So the following table gives the values of CV for an orifice of 10 mm diameter with the corresponding head. So if head increases, so there will be, you can see the difference in CV. If you have 20 mm head, CV is 0.959, and if you have head is more, 0.994. So head increases, CV increases. Its average value is 0.97, close to 1. Okay, the theoretical velocity is very simple to calculate. It is under root 2 GH, simple. H is the head of water at vena contracta. This is H, from the center of the orifice to the top of water level. Again, coefficient of discharge is the ratio of actual discharge through an orifice to the theoretical discharge. Actual discharge you can find in the field or by experiments. Theoretical discharge is the formula. Okay, so CD is also defined by the product of CV and CC. So its average value is 0.64, from 0.60 to 0.64. Coefficient of resistance is the ratio of loss of head in the orifice to the head of water available at the exit of the orifice, is known as the coefficient of resistance. Okay. Mathematically, this is loss of head in the orifice and head of water available. So the loss of head in the orifice takes place because the walls of the orifice offer some resistance to the liquid as it comes out. So we know that when the resistance increases, the loss of head also increases. So the coefficient of resistance is generally neglected while solving the numericals. So these are two numericals, the problems, and you can see the answers are also given. So it's a very simple problems. You just put the formula and you will get the answers. Okay. So this is all about this lecture. So here we're going to